we try to that everybody tries to get access to this repository. I have to say this went pretty slowly and pretty complicated because I would say everybody tried to send me the information via a different channel and in a different way and on different dates and so on and so on. So this was not nice. But in the end, I have to say this is it's not too bad. Like somehow let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 people managed to get a JSON file up in the repository. Yeah, we just have to figure a bit out if okay, if you can work with that. And yeah, the remaining people who didn't commit didn't upload a JSON file should really try to do that. If you don't have the GitHub access yet, please send me your GitHub login. And if you have issues to upload that, then I can just support you, and all my students can support you in doing that. Okay, biggest issue I have so far is let's see. Okay, was one file which is here in the wrong spot. Well, that's not too bad. We can just delete it because it's also in the right spot. So I will just pull the latest changes. Okay, we got another one, so this is good. So here, okay. The second thing is okay, man, I don't like that the names are all over the place. It's more like, okay, we should try to like stick somehow to some convention, and I would say okay, let's just basically first name, second name, and use a underscore and keep everything lowercase. I think this is also important. Like if we try to do like working together on the data, basically everybody should try to somehow stick to the same way of doing things. That's really important because otherwise it becomes really complicated to work with all this information. Okay, for now, but I would say I'm pretty happy with that. I would just quickly update the names and just check if the files look okay. This looks okay. This doesn't look okay because basically this is my information. Oh man, where? Well, what happened? Okay. Let's see. This is all starting really good here. Okay. Let's see. Is Bea here? No. Ah, yeah, Bea.
Yes, I'm here.
What happened here?
Sorry.
That's my information, not your information.
I forget to push. Sorry.
Okay, perfect. Okay, so let's see what is like. This is really it's really 10 people. Everybody's doing something else. It's like this is my life as supervisor here. Seriously, this is my week here. Like everybody's writing me on different channels and doing different things. And I have to try to somehow coordinate that. This is really fast up. This is taking a lot of energy. Okay, let's quickly walk through the files. I think this is just an exemplary. Like the good thing is like basically everybody could add the information. Somehow this looks like there's less information in there. Okay, site is okay. Okay, Bea, are you updating the information? Then if you had a computer with Git right now. And so looks good. This looks okay. We have to check if this files are okay. Here, okay, this is pretty okay. It just has the first name. Okay, that's hopefully okay. Looks good. Okay, this is the formatting. Otherwise, this looks good. This looks nice. Okay. Looks good. It's good. Okay. Nice. Okay, that's also interesting because now you see basically that I have a conflict in here. It's just like that a file is it basically has the same names. So this is not liking the merge, and so it's basically not overwriting the files but creating both files. So Darius probably fixed this right now, and we can just quickly check if this looks okay. So we will just remove the one, it's duplicated, good, and skip pull. Okay. Let's see. Conflicts, but you're still merging. You skip commit to conclude. What? Oh, and now it should be able to push that. Okay. So this looks pretty good. One thing I didn't like so much is the formatting, but this is just because often with these formats you should just basically try to keep the formatting as nice and the indentation as nice as possible. We will just quickly fix this here with a different tool. So git XResearch authors. Okay, so I'm just opening this, and basically here I can basically just fix the indentation on naming. Basically, if I save, you see like this fixes the formatting and the indentation of the files. Okay, most of this looks good. There's no it's better. Okay. So okay, pretty happy with that. And just okay, pretty nice. So we would check if we can. Normally, I would also try to pass the information, but for now, I'm waiting until the others committed the files. And so what we would do today is mainly talk about trying to figure out what Amipril is and what it is doing. And that's by reviewing the literature, which we started with. So this is basically how you normally figure. I would just go through the process of figuring out what Amipril is, how it works, what the pharmacokinetics is, and just start by reading the publications. So we did basically this research and got this list of publications which are about Amipril and lisinopril. And now we would walk through the publications and see where we have pharmacokinetic information and what we can learn from that. So what I'm second. What I'm normally doing is that I have one document where I try to document all the information about the substance and all the information we can figure out. And so for now, we don't know much about Ramipril. I think the only thing we figured out so far is that it's converted to ramiprilat. and that it's an ACE inhibitor, but I don't think we know much more. So okay, I will just add the link to the document in the README. Well, here you would basically, if you find any information about ramipril, you would just add this to the file. You should all have like access to add information, and I'm basically getting notified, and then I can just accept it or like format it and so on. Okay, so normally how I start is that I basically just go to Wikipedia. Sounds like not very scientific, but normally it's a pretty good start for many things, or at least it gives you a feeling of if there's a lot known or not much known about things. So often it's not the content, but the length of the article. So okay, donations right now. Right, so the main important thing is, I would say here, you already get nice information about the substance and links to databases here to the right, which is very useful. And you also get like some interesting information up here. This is, for instance, for us, like immediately like really important information here. Let's see if we can make it a bit here. Like for instance, we see things like bioavailability. This means given oral dose or intravenous dose, how much will be the difference in the area under the curve. And if basically if a drug is not completely absorbed, or if it's metabolized in the intestine or in the liver before it reaches the systemic circulation, then you have like a lower area under the curve if you give something orally compared to intravenously. And this means basically the bioavailability. So if you would give, it's a 10 milligram ramipril orally and 10 milligrams intravenously, it means only 20% of the AUC of the oral dose is appearing compared to the intravenous dose. Okay, I hope this makes sense. But another important thing is always protein binding. It means basically if you put the drug into the system, how much is it binding to proteins in the blood? These are mainly like high abundance proteins like albumin, bilirubin, sometimes the apolipoproteins and stuff like that. But this means that you have a lower free concentration, and here it means 73% of this drug are protein bound, and like the remaining 27% are free. Metabolism in the liver, this is good. So ramiprilat, this is what we guessed last time, and we built like a first model in the liver. So we were lucky. Could have been also somewhere else, but like I mentioned in the introduction, most of the time the liver is the main metabolizing organ. We have something about the half-life and the excretion. Here, this is also very nice. It's like it shows us kidney, 60%. This means the kidneys are really involved in the excretion of ramipril. And we also have fecal excretion, which is like somehow in line here with this low bioavailability. Yeah, it most likely means, okay, not all of ramipril is absorbed while it goes through the intestine, and just like a pretty large amount, like 40% of the dose you give orally is directly excreted in the feces. And this means that like basically not only 60% are absorbed. And of the 60%, probably also some is metabolized in the liver, and that's why you in the end you only have a bioavailability of around 28%. Okay, so these are not the perfect scientific numbers, but these are really good house numbers to get a feeling what must be in the model, what is important, and it's more like also for checking if the model makes sense and if the data makes sense, if you have such numbers in the back. So okay, let's just we would Pharmacokinetics. We'll just put something here. Just copy this in here for now. We would definitely make a section about pharmacodynamics. here things would be like basically effect on ACE, like the inhibition, but also like lowering of blood pressure, heart rate, and so on and so on. This would be all here. Pharmacokinetics would really be what I presented in the pharmacokinetics part. Okay, this looks pretty good. What else can we take away from here? I would say the important things are like the mapping to the databases. Yeah, this can come in handy for the annotations. Like last time, I don't think we did the annotations for the models. So we could quickly do the annotations with this information. So we had this liver model, and we had some annotations in the model for plasma and liver and so on. But we didn't have annotations for our ramipril and ramiprilat. So we could basically use this information to define here the annotations. Okay, let's quickly do that. Annotations come here from our annotations. These are compartments. Probably we have already also some. Where's this coming from? Sorry, I have to quickly check where define that. It's basically here. Here we have the annotations, and we would add a section for the species, where we can look up our species annotations. And we definitely want something for the real, which is our ramipril, and we want something for the rat, which we define in the model as our ramiprilat. Okay. Normally, good annotations for species are to chemical databases. Let's go back and see here. Good chemical databases are definitely KV, which is a database for mainly small molecules. And this is normally a pretty good annotation. So we would definitely use this here. Ramipril, this looks good. It's also a nice description. And we would just define here, okay, the real means in our model that this is what is defined as a KV. And then we need the right term. I hope this is this. Okay. This would be basically this. And we would use also some other annotations. Basically, what I really like is the where's it? PubChem. Here we have the PubChem, because this has many links to other databases. So this is a pretty good identifier, and it clearly says what our substance is, which we're talking about. So this is a PubChem compound, and has this identifier. And what I normally also take is the INCHI key. This is basically this here. This is a hash key, which uniquely not perfectly uniquely, but this is basically a hash key for the 3D structure. So this is, I would say it's practically unique for the 3D structure. There are like larger things like like the real INCHI key and more complex things, which really describe how all the atoms are like connected. And this is just a shorter hash key, which describes the 3D structure. So what we have with this annotation is basically telling us, okay, this molecule we're talking about has this structure, but basically 3D structure with a right. Oh man, my organic chemistry is a long time ago, but you have the cis and trans bonds and so on, and this atoms can be on different sides and so on, and this is all described in this key. Okay, long story short, this is basically just giving us the 3D structure in a simple string. And later on, we can map this model component to this 3D structure. Okay, this was the INCHI key. And then we would do the same thing for the ramiprillate. Yeah, ramiprillate, there will probably, if you now look for ramiprillate on Wikipedia, you probably will find a very short entry, because this is not a main substance you give, but this is just a metabolite. And so you see, you basically don't even have an entry for that, despite it being a real chemical and everything. But this chemical databases like PubChem, they have, of course, these entries. So ramiprillate looks good. So exactly. So this looks pretty good. This is most likely our product we have. But this is our product. It makes like a quick 3D, a quick structure check makes sense. If you look at this, looks something you have like this. Oh man, I forgot all my organic chemistry. This is a benzene, like this ring, and this aromatic rings here. And if you look here, you see you have the same rings. So this is most likely the product. Also, like the molecular weight is not too far off. You see here you have 416, and something is like removed from that, and then you get ramiprillate. Most likely it's oxidized. So, and you get then this compound here. Okay, this is the right thing, and we just add it to the annotations. And this is our ramiprillate. We look if there's a KB. Here's a KB mapping, so we can get the KB identifier. This is 77363. That's this here. And then we just need the INCI key from the structure. This is this here. So, okay. And this, what we basically now did is we just defined what our model components mean. And then we use this to describe our models. Especially here we say our annotations. It's basically from our annotations files in the species, we're taking the real and getting then this annotation information in here. Okay, this is a rat. This is a real, and this is a rat. Okay, perfect. And then we can rebuild the model. And if you, I will quickly load this in this SPML utils just to show that we now have the annotations in there, the SPML for humans. Results. And I would upload the model. Drag and drop. This is working. Yeah. And if we now see that we're clicking on here, we see that we basically get a lot of additional information. We just put the annotations in here, but via these annotations, we can resolve like a lot of descriptions, like this is a prodrug or for ramiprillate, active metabolite obtained by hydrolysis of the and so on. An angiotensin converting enzyme inhibitor, and so on and so on. And we get also the mappings to other information and to other databases, get synonyms and so on. Like synonyms are often important because, like, if you sometimes you will read ramiprilium or altase and so on, but this all means the same. This is all ramiprilium. Okay, but that's why how we got via minimal information, we got a lot of additional data in our model and clearly describe what these compounds are in the model. Okay, so far so good. This is where this annotations come in Formula molar mass. Okay, this we need at some point. We need definitely the molar mass. For now, it's not important. Okay. I think the important name is here this altase. So if we see this, this is basically a synonym of that. It's an ACE inhibitor. More than 2 million prescriptions. Okay, this is all not so important for the model. Medical uses is here the high blood pressure. This is important. Contraindications. This is always important. I can see. Okay, yeah, hypotension. This makes more sense. If you have hypotension, you shouldn't take a blood pressure lowering medication. Okay. Kalemia. Okay. Here, mechanism of action. This is probably interesting. Yeah, so I would probably just copy that for now. What's relaxation, smooth muscle, needing total reduce blood pressure. But this is basically what you've all figured out in the first week. Here, the next sentence is really important. Ramipril is a prodrug or precursor drug, is converted to the active metabolite ramiprilat by this here. And ramiprilat is mostly excreted by the kidneys and so on. Okay, so this is all really important because now we learned that the real drug is not the ramipril, but the real drug is the ramiprilat. And this is important if we couple this to the pharmacodynamics models. Okay. So we will just do a general introduction section here or general information. Okay, it's always important to, if you copy something from somewhere, always use the sources. I think this is the most important thing. You can copy whatever you want, just state the sources. And this is especially important later on if you write the article and so on, because everything which we write in the article, we have to write ourselves. Like we can collect a lot of information, like copy paste, but we can't copy paste things in the article. So always state the sources, and this is also important later on if you want to say, okay, where do I have the information from, and how credible it is, and so on. That we have the source. Okay. Normally, I'm normally not doing this exactly like that, but I think this is just good practice. Normally, if you use web links, you should also add when you access that, and that's it. Okay. And basically the same for that here. And yeah, this document doesn't have to be very clean or anything. It's more like, okay, a job for important information for now. And I think here they really there's two important informations in here. Ramiprilat is mostly excreted by the kidneys, and ramipril is a prodrug, active metabolite ramiprilat. And this enzyme here is also important. And this will be important in the pharmacokinetics part. So we will add here some sub things. We need definitely like some excretion information and metabolism. This is like all this ADME I told at the beginning, that we have to figure out what is the absorption, distribution, metabolization, and so on of our substances and drugs. So we have to figure this out. And here it's metabolization. So important information is definitely here. This is excreted by the kidneys. Okay, and this is and this belongs to excretion. But we also had like the other information here. Yeah, ramipril is excreted around 40% via feces. Okay, 40. And 60% via the kidneys. And metabolization This here is important. Yeah, because this is an enzyme I have no clue about. I never heard that. Well, I heard it before, but I never did anything with that. So this conversion ramipril to ramiprilat is most likely in the liver via this enzyme here. Okay, what else can we figure out from here? Some patent, brand names, research. Okay, not much more here. Okay, but this is it's a good starting point. I would definitely have a look at the enzyme now. Where is it? Enzyme here, this one. Yeah, this sounds very liver located. CES1 gene is also important. Serine esterase. Okay. Okay, this is all really important. Basically here all for the metabolization. Just copy that here. Okay. Okay, so this is pretty good. Because then we already know, or already we learned like this conversion here. This is basically what we what is catalyzed by most likely via this reaction, via this enzyme. Okay. So far, so good. I think this is what we can learn from Wikipedia. This is normally it makes sense in the clinical significance. Okay, here's more information. We probably have to go back to that. This becomes perhaps important if we have like drug-drug interactions and so on. But for now, okay, the important thing is that we just remember the name carboxylesterase 1. And if we see somewhere CES1 or CES1 or something like this, then we know, okay, they're talking about this enzyme here. So like always, if you look at enzymes, it's important to understand if there are diseases or special things. This is interesting that he's certain cancer, this is altered. Here there's an inhibition by organophosphates. This could also be interesting. Okay, activate. Here, and CES1 is responsible for the activation of many products, such as angiotensin converting enzyme inhibitors and also other stuff. And here, genetic variants of the CES1 can significantly affect both pharmacokinetics and pharmacodynamics of drug metabolized by CES1. Okay, and this is really important. And it's also involved in heroin and cocaine metabolism. Okay, probably not so important for us right now, but okay. But this is like a common pattern. What you see, there's only a certain subset of enzymes we have which are converting things, and they're often involved in many different things. So I would say the most important thing here is that there exist genetic variants of the CES1 and they can have a strong effect. And this could definitely be an interesting application of our model, that we look at, okay, what is the effect of the changes in activity of the CES1 on ramipril and ramiprilat pharmacokinetics, and how does it affect pharmacodynamics and so on. So this is definitely something which is interesting. So for now, I would just also just write this down here. Okay. Yeah, this is this genetic variance. And yeah, what I'm not really forgetting it. Just adding also adding a comment. Okay, so far so good. This looks all promising, but this is basically how you build such a model, that you try to put the building blocks together. And so definitely what I took also away from this information so far, that we definitely have like we need a kidney model, because there is some substantial excretion of ramipril via the kidneys, and the ramiprilat is most likely also excreted via the kidney. Here ramiprilat, at least it's said like on Wikipedia. Who knows how true this is, but most of the time this is pretty, like, it's good information. How quantitative this is in the end, we have to figure out. Okay, so different, obviously I think what I would do now is like quickly build a kidney model just for the excretion. But this is, I would say, one-to-one what we did for the liver model. That is just a bit simpler. And then we would go to Zotero and look at the literature, what we can figure out from the pharmacokinetic literature. This is normally how you go through that. Okay. So we have already we have the liver model. So we would now build a kidney model. I would just create a new, probably I would just copy what we have, because we can reuse a lot of things for the kidney. It's basically, in the end, this is, it will be similar, because if we look at the, I don't have the figure here. Yeah, no. Yeah, because it's, like I say, it's also an organ which is just in the systemic circulation. So blood is going in the kidneys, it's filtrated, and things can be removed and excreted in the urine, and then the remaining blood is going back in the venous circulation. So it's, the liver is a bit more complicated, because it can get blood from the gastrointestinal tract and the hepatic artery, but in the end it's more like blood is flowing into these organs, and they can take up the substances and excrete them or convert them, and then the blood is leaving the organ again. So it's basically just another organ, and so it has a pretty similar structure, like from the model character. Because we have to change a bit the whole thing to kidney model for the ICE. This is of course the kidney now. A lot of model for renal, and this is ramipril and ramiprilat excretion. I assume there's no, most likely there's no metabolism anymore. It sounds also like this because the enzyme was already called liver says. If I have to guess, I would say this is not appearing in the intestine and the kidney, because many of the enzymes which appear in the kidney can also appear in other organs, often with less activity. But if this already was called liver says, I would basically guess there's no metabolization in the kidneys and also in the intestine. Okay. So, okay, this is not a, okay, also these are not dummy models. Okay, liver model. Just remove the dummy. This is already getting better. And in the kidneys, we also have like, it's very similar. We have plasma or like blood, which is going through the kidneys. We then have a kidney. And the volumes should be smaller. I'll quickly have to look this up. Okay, yeah, the kidney model. No. Okay, in the end, it doesn't matter because this will be in the end overwritten by the whole body compartments. But don't give too much on this values. And I can quickly figure out how much kidney we have. We have normally, let's see. Yeah, normally around 2% of our body are kidney. So there's a bit less than the liver. Liver is normally 2.5% of the whole body is liver. Kidney is a bit less. It's only, what am I saying? Oh, okay. Sorry, this was totally wrong information. Don't believe anything you hear. Okay, no, totally wrong. We are only, what, 0.4% of the body. Okay. Okay, 0.4% of body weight is approximately the kidney. So if we have around 70 kilograms, like a reference human, and 70 times 0.4, the density of around 1. Okay, what am I doing? 0. Yeah, this is percent. Let's take the exact value. Okay, so we have around 300 grams of kidneys. I don't know. You build this human model is probably it's probably if it's the liver is pretty big, so the kidneys are much smaller. Okay, so around 300 milliliters. This is of course the kidney now. Kidney, plasma membrane, and then we have ramipril in the extern. We have the ramiprilat in the extern, and then we have the whole thing in the kidneys. I have to put it into the kidney compartment. It's in the kidneys. I have to fix the annotations. I did already. Okay. So now what we did, we basically have the substances in the external and in the internal compartment. And then we only need 2 transport reactions. So here, okay, I would remove that. And then we just have to rename the, basically we have to add the urine and excrete the whole thing in the urine. Okay, let's add the urine. There's an additional compartment. I just did a bit of copy paste here. Sorry, but this is okay. Basically, we just say we have urine and we have an we give it like this 1.0. You don't have to give anything about that. We just say we have 1 liter of urine, but what we in the end just need is a compartment where we can put metabolites. And in the end, we just track the amounts which are in the urine. So we can't track the concentrations, because of course you build new urine all the time and so on. So it's you don't really have a concentration, but this has a large, it has a turnover. So we are just interested in this as a compartment where we can put substances via renal excretion. Okay, and then we have to, of course, to put also the we have to excrete these two in the urine. We would put the real in the ramipril in the urine. This is a urine compartment. And now what we're doing here is that we're tracking the amounts in the urine and not the concentrations. This is basically what this flag is doing. This is an amount now, and that's in the end we're just interested in the millimole of the substance which appearing in the urine. Okay, and we're doing the same for the amygdala, and then we just need the reaction for the urinary excretion, and then we should be good. Because we're not really interested in what the kidneys are doing, we're also not interested, okay, what are the concentrations in the kidneys? So we're really just interested, okay, what amount of is appearing in the plasma in the kidneys, and what is later on appearing in the urine. So we're not really interested in this internal concentrations. We would also delete these two. We only have basically in the plasma these two concentrations in the urine, and what the kidney is now doing, that it's excreting it in the urine. So we will have an PLX, which is a ramipril excretion in the urine. X, and this will just use the RIL in the plasma and irreversible put this in the urine. And this is located in the kidneys. Transport reactions, and then we just need some parameters for that. And in this case, we need not a Vmax, but a K parameter. Okay. Always, like, if you have questions, just ask. A lot of these is a bit fast, but this is we're just basically adding a process which is taking the substance in the kidneys and putting it into the urine. This is basically here. This is just a rate for the urinary excretion. Of ramipril. And this is the kinetic constant. And then we have a simple equation for that. This is now our K value, our real XK scaled with the kidney volume. And this only depends now on the real external concentration. So this is just a basically first order kinetic, which is proportional to the actual concentration we have in the plasma and the kidneys, is excreting that in the kidneys with a given rate. That's basically it, and we will do the same for the ramiprilat excretion. And here we just have to change all the basically changes to rat, and ramiprilat, and real becomes to rat, and that's it. Ramiprilat. Okay, and here of course this depends on the rat. Okay, I will quickly start Cytoscape, that we can have a look if this is looking correctly when we build it. And then, of course, this is now our kidney model here. And we're building here the kidney model and kidney. I quickly have to check if we have somewhere liver still here. No, looks okay. So let's see if this builds. So we have still some errors in the model. Yeah, so here it's basically its parameter was defined 2 times. And this is basically the problem because we didn't define the parameter correctly here. So this parameter here, and here we define the parameter. And then here looks a bit better. And then here it references this species, which is not defined. We have to check if we really did this species correctly. No, we didn't, because we didn't give the right IDs. So basically the real in the urine and the red in the urine. Okay, let's check. Okay, and then let's build this very simple kidney model, which is not doing much, but just basically taking the concentrations in the plasma or the amounts in the plasma and excreting that in the urine. And we can imagine if we couple this to our liver model, which is converting the ramipril to the ramiprilat, we can get already like a lot of the effects, a lot of the information we saw in the other in Wikipedia and so on. Okay. Quickly saving this. Also here you see you should always pull the changes first. So Bea and Helen added the things. It's nice. So quickly check that. Okay, this looks good. And Helen also added information. Okay, looks okay. Okay. Okay, so let's go to Zotero and try to figure more things out. It's like I think we know some things about ramipril, but not much yet. What I did today, I went over a few papers here. I will just quickly show how this works and add the information then to the additional paper. So if we just start at the beginning, it's more like, okay, here we see, okay, this is in horses. Okay, so we don't like this. But it's sometimes good to just scroll over it. We're not interested too much in horse data, but the interesting part is that there is pharmacodynamic variables. So they received these different drugs. So what we can learn here, there are definitely different drugs which you can use in horses to ramipril. And then there are this typical, these are typical pharmacodynamic values. We also have AUCs and something like T-halves, but also like some maximal effect of the dose. Always have to understand what is measured here. Yeah, and I don't really have any clue what is measured here, but okay. But the more interesting part is here what we see in the inhibition. This is and it shows like some inhibition in percent. So we see like okay, there are these different substances, and okay, you have different amount of inhibition, and the inhibition changes over time. okay, not too much to learn here about, but we also see yeah, a bit of changes in blood pressure, but this is okay. This is I'm not sure, not too impressive, but it's probably what we want somehow. But you see here, like that it's not going down too much. You're getting your blood pressure from 120 to, I don't know, perhaps 110, 90 to perhaps 80. There's not too much changes. Here you get around 10% change if you have like 20 to 70% inhibition of the ACE. So these effects are not too big. But I would expect in human this can be different, but this is probably what we have to think about also in the pharmacodynamics of humans. So this would probably be, I would be surprised if this is more than 10 points or 20 points in the millimeter Hg. Okay, what else can we take away here? I would say not too much. It's just okay. It's just that there's a lot of horse research because this is basically like because you want to dope your race horses to run faster. And like one thing is definitely stress management in race horses. So like there's a lot of research in like in stuff like that in horses also. Okay. I will just go through that. What we okay. What can we learn from this paper? Yeah, this is basically just saying some combination in red plasma. I can show you there's nothing in this here. They just looked at rats, and that's it. Yeah, basically everything which I already did checked, and low priority we don't have to look at. The Aliquini, there's a one paper we looked already at, and I think here the important part was really the different time courses of the ramipril and the ramiprilat. The ramipril peak is very fast in a few hours, and then the ramiprilat is like really over over 15 hours or so. The peak is much longer, which makes also sense if you want basically this is the active compound, and this is like really the ACE inhibitor, and you don't want something which you have to take every 2 hours to get a good effect. So you want you take this is converted to something which has a much longer half-life, and then this is basically should be the right effect. Okay, so this is pretty good. So I would for now just copy that we have it in the other document, and it's just for now that we get some reference curves and some general information in here. So this would be here under pharmacokinetics, and I would add this study name. I think this was in 2019, and just make this a bit smaller. Okay. Okay, what else can we take away from this paper? I think it's not too much. It's a really good paper for the calibration of the model, but otherwise there's not too much information in here. It's more like it's very nice data. The main thing I said also last time, we have very large error bars, especially because these are standard error measures. Otherwise, not much to take away from that. All the other stuff was here. There was no information in here. Here, there was something about ramipril in renal failure. You can see 6 subjects, and they have different glomerular filtration rates. This is a measure of kidney function. So they basically took, I assume, 6 subjects which didn't have too good kidney function, and then they checked what is going on. We have here some pharmacokinetic parameters, which is nice. for ramipril and ramiprilat. So this is pretty good. And we also have some pharmacodynamic information here. Pharmacokinetic.
In figure 2, is there supposed to be another line, or is it very blurry? Like I can't really distinguish that.
No, this is good. The error bars are a bit thin, I would say, but there should be a line here. These are the error bars. No, this is
okay.
Yeah, but it's yeah. This is not a like, let's say, like this is a plot which will hunt somebody of you, whoever selects this paper. So I can assure you that. Especially if you just look at the axis, like, man, they just every data, like this is not a normal axis, but they are just like, okay, here's a 1, 2, and then there's a cut, then there's a 3 and a 4, and oh man, this is all very strange. And this is also hours. We can see again, like after a few hours, this is going pretty down after 3 hours. And then we can see here is the ramiprilat going up. And that's an interesting part. And then it stays pretty, it goes down over 3 to 5 days. Okay. This is also like interesting. And especially if you take one of these, yeah, well, it has a pretty long half-life, the ramiprilat. I think this is really what we have to take away from that. And this is of course dangerous also for drug-drug interactions. And if you take multiple doses and stuff like that, for instance, if you forget to take your medication and then you take 2 and so on, this is like, oh man, there's a lot of dose addition and so on. So there's lots of interesting things going on here. But otherwise, this is, I would say, pretty in line what we saw in the other plot. This could be a bit different because it's in renal. This is in renal patients. That's probably also because the half-life. That's why the half-life is a bit longer. Like here we saw after 2 hours, this is going down. There it was 3-4 hours. This could definitely be something. So for stuff like that, it's just writing this down. Normally I'm doing a section about disease or interesting applications. And here we will do some renal impairment. And we will just write down this publication for now that we're not forgetting. It's basically this OWL 1987. So there's definitely some data in there. But overall, this general feeling of ramipril is going up first and fast down, and ramiprilat is coming up and staying up very long. This is confirmed here. What I found really interesting is this plot here. This is now like here we see serum concentrations of ramiprilat, and here we see the inhibition of plasma ACE. So this is really what we're interested in the, or this is one key component of this model we want to build. We want to understand, okay, now we give ramipril, it's somehow converted to ramiprilat, the ramiprilat is in the system, but how's the ramiprilat inhibiting the ACE? Basically, and then we want to understand if we know the ACE is inhibited, how is the blood pressure going down? So this is like, we would say, like this is a key puzzle piece for building the model. And it basically shows if we have serum concentrations of ramiprilat, then our ACE is above, I would say here, above 10 nanograms per milliliter. Probably, if you can read this axis, like I think it's 10 nanograms per milliliter, then you have 100% inhibition of the ACE, which is good. And it looks also like a pretty nice curve. So this is really like something important, and it's also, yeah, always like to see if we see this in this. Yeah, okay, but 10 nanograms is a lot. That's also the problem. Like if we see like, okay, well, let's say here, perhaps 8 to 10 nanograms per milliliter. But if you look at the typical dose of ramipril and ramiprilat, then we see we don't go really above the 10 nanograms per milliliter. So here in this area, like, I don't know, 2 to 12 hours, you probably will have a 100% inhibition of the ACE. And then here with the 5 nanograms, we're at 80%. And then here after 2 or 3 days, if you had 2 nanograms, you're somewhere here, probably 40% inhibition, something like that. Okay, but this shows like, okay, this relationship between pharmacokinetics, okay, where are your plasma concentration curves? And then, okay, here the pharmacodynamics, how is your ACE inhibited? Okay, this is a super important plot. And this is also something which we will probably use to build our model, because we will just use this curve to model the pharmacodynamics. We have to be aware this is in renal impairment, but it's like already something really interesting. So I will just also put this 1987. This is basically the inhibition of the ACE. Okay, what else can we take away here? Yeah, this is also very nice because we have here a time course. And this is probably, yeah, this is in line what I said above, like just trying to bring together the pharmacokinetics with the pharmacodynamics. It's basically, okay, you see an almost 100% inhibition over the first 24 hours, and then you go up to 40–50% after 2 days. So this is what you typically see after a dose of ramipril. And then it makes also sense if you take the next dose after 24 hours, then you will probably stay down very low. For me, like really surprising is it's normally not very good if you inhibit things like 100%. So yeah, and also like if you inhibit something 100%, you normally expect like strong effects. So okay, if you inhibit this key enzyme, the ACE, by almost 100%, why is the blood pressure going down only a little bit? I think we see this also here in the, we see this here, but here the effects are much larger. Okay, these people are starting at something 150 systolic blood pressure. Sorry, these plots are really, you have to believe me if I say numbers here, but this is the 150 somewhere. And you see like after the 24 hours, you see a drop to around 130. There's not so much effect on the diastolic blood pressure. This is going something from 90, okay, to 75 or something here. And then after the 24 hours, we see also this is recovering. But also like, this is also something typical that we still see, you see a lot of noise in the whole things, like a lot of fluctuation, lots of error bars. These are not clean curves, like this is going down. And this, of course, goes also through to the pharmacodynamics. This is not like a nice, okay, like, yeah, if you just look at the inhibition of the enzyme, this can be quantified very easily. But the blood pressure has like lots of effectors. Because if these people are scared, or I don't know, or like like remember like measuring the blood pressure like in this setting in the room here, it just there are a lot of factors which can influence the readings here, and so this is much more noisy. But overall, this is I would say this is pretty good data. Keep in mind that this could all be renal patients, but I would say a lot of things can we take away. Like for instance, this dose response curves, I would expect them to look identical in healthy patients. I would be surprised by why would the ACE inhibition in renal patients be different? Who knows? But yeah, this is basically really good data to just get a feeling of what are the effects we expect, and the timescales we expect, and what our model should do in the end. So probably we want our model to be able to do something like that here. that it predicts the inhibition and that it predicts, okay, the drop in systolic and diastolic blood pressure. So somehow we have to model that, but for that we need those response curves here, and we need a bit of data here to calibrate the model. Okay, just dropping that in here, that we're not forgetting that. And this is mainly what this document is for. It's just, okay, this important things which we find somewhere, to put it all in one place, and then use this as a starting point to build a model from. Let's see, where's the tail here? Just to check if there was anything else in the model yeah. That's basically it. But this would be definitely a really important paper, because it has really the pharmacokinetics and pharmacodynamics. But the big question mark is a renal failure, but okay. I think there's similar data also for healthy subjects. Now, here's another study. Here they looked at some vasopeptidase inhibitor, AVE something, but they compared it to ramipril. Okay, I think the interesting part is here again that they measured some time courses in ACE in activity, and basically you give the different drugs, and one of these drugs is ramipril. In this case, the ramipril is the diamond here. Diamond is 10 milligrams ramipril. So this is typically what you see after a dose of ramipril. It depends on how much was given here, but it's very similar. We see basically 100% inhibition of the ACE, and yeah, this stays at least for 12 hours, like very inhibited, and then it goes down to 50%. Here it's like the recovery is a bit faster, but it could be just different doses and so on. Also interesting is here that they measured something which is called ACSDKP. I have no clue what this is, but this is could be important. But this is more like this is what you have to take away from this literature review. You have to basically collect all the breadcrumbs and then see what is important for the model and put it together. And so this collection is the important part, basically, that we see similar things. This is always good if different publications shows different things. It could also be that because here we have healthy subjects and you have more renal clearance, that the ramipril is faster cleared from the system, and that's why the recovery here is faster. That in renal patients you will have an inhibition of 1 to 1 days of 100%, but in the healthy not, because the ramipril is just removed faster from the system. So there's like a lot of, I say, like this could even fit with the other data set, and explain the difference between healthy subjects and the recovery and the renal patients. Okay. Well, this is we'll just put this here also. We have to store this was a CZ something. Okay. Putting this here for now. I think the important part is if you just look at, okay, this is now a bit small, but if you just compare here this diamond curve, okay, there's a bit different time scales and this here, and this is just down a lot longer and then goes up, and this goes faster up again. But you see similar things, that is almost going down to 0% ACE activity, and then you see a recovery afterwards, after the time. Okay, this looks all very good and very consistent. I like that. And it looks also like very nice that we didn't see any other substances so far. Here you see also like yeah, they measured a lot this urinary proteins. I'm not sure this could be important, but at this moment I have no clue. I'm looking more for pharmacokinetics and pharmacodynamics in the first round, but of course I measured also things like active renin and decrease in MAP, which is mean arterial pressure, which are important readouts. Yeah, but this is we have to look in more detail if something of this is important. And this is just this AVE 8048, which we're not interested in. Okay. Yeah, let's do one or two more papers. I will show one or two more examples how you normally go through that. And yeah, it's most of the time I just look at the figures. First a bit at the title and the figures and see if there's something useful in there. Here it's the interesting part is, okay, we have something ramipril or ramiprilat here, and also other substances. Atenolol is also I think a beta blocker. Valsartan, candesartan, and we have pharmacokinetic parameters, so this is good. Interested in that. And we also have time course data. Here they only reported the ramiprilat. Yeah, but we see similar thing that this stays up like very, very long. Basically here this looks like after 48 hours. This is not going down at all, which is it's probably what you're interested in such a medication, that you take it and then it's like you only take it every 24 hours and you get a pretty flat pharmacokinetic profile. Yeah, but this basically means that you don't have too high renal clearance of the substance, and that it just stays in the system for pretty long. So it's converted to ramiprilat, and then you probably have a very low renal excretion over time. And this just takes probably a week until everything is out of the system. What else do we have in here? Oh yeah, exactly. This was an interesting plot, because here they plotted the basically the changes in plasma renin concentration and how this is changing with ramipril. There is some relationship to the plasma renin concentration. Okay, we saw that the angiotensin is an important player in the renin system, and this is probably it's angiotensin, and then it has something to do with renin, and then it has something to do with blood pressure and so on. So having a relationship between ramipril and this changes in renin is also important. But I'm not, at this point, I have no clue what to make out of that. But it's mainly because I don't understand the pharmacodynamic system well enough. But it's for me, it's more like this is a hint that this could be really important, and also that you see some similar relationships between different substances and some linear relationships. This is always a good thing, also like for including things into models. Okay. Let's bring this also in the other document. I need the name for that. This was Assisi 2013. Okay. Yeah, this is basically how one collects information. So the key part is now really to go through the through this literature. So I sent you all invitations to the to this publications, and so what we will do next week is basically that everybody is starting with one publication. So I have to figure out like one publication for everyone here, and hopefully they have a look for publications which are not too difficult, and then you have to basically read the information in there, and you're responsible also like for curating the data and so on, so that we can bring all this different pieces together in the model. Exactly. So important thing would that you really get access to the Zotero and have a chance to look at the publications here, and then I would make a list that everybody is assigned a publication just randomly, and then you would try to understand that, and then next week we would try to start getting information out of these publications to improve the model. Okay, I hope this made sense. Today I tried to show a bit, okay, how are you building these models, and what is the typical process? So a lot of this is just going through the literature, looking what is in the literature, and trying to bring this, getting a consistent understanding of what is going on, and also like to understand what you don't understand. Like for instance, I know like I'm pretty sure about the whole pharmacokinetic part, but I'm pretty unsure about the whole pharmacodynamic part. It looks pretty consistent. It looks like, okay, the effect from the ramiprillate on the ACE inhibition is pretty clear. And we see also a clear drop in the systolic and diastolic blood pressure, at least in this one publication. Okay, how this is all connected now to renin, and what is the exact mechanism that the blood pressure is going down? This is a big question. But yeah, we have to see how much in detail we're going to model that. Okay, far so good. Are there any questions so far?
I'm sorry, did I get you right that you will give us already the article we should read? Or should we?
Exactly. No, I have to select that. The problem is like, the point is like we really want, we have to go through all these documents to figure out which are the 10, 15 best publications with the most data for the bug, and then we will take that. But for that we have to look at all of them. But for me, it doesn't make much sense because you haven't ever read such literature. So it makes more sense you click a bit through and see what is the heterogeneity. What do we find in the publication? But don't spend too much time on reading all these publications. Just have a bit of look to get a feeling what's in there. And then I would select like publications, and everybody would read their publication and present what's in there, and curate the data from there. Does it make sense?
Yeah, okay.
Exactly. But one is feel free to go in the literature and also add the tags and so on, and also this is if you want to contribute more, you can contribute more. This is more like some people also already try to build the models themselves and simulate stuff, or not simulate, but like try to get the model scripts to run. So there's a lot of things you can do if you want, but basically it's I think the most important thing is that you do the one study or two studies papers you assigned. And I think this is the most important part, that we get that done before this one blog course. In the blog course, we would bring all this data and information together and improve the model. Okay, more questions?
So actually, yes, regarding the blog course. So now there are 2 blog courses established. Well, the idea is that they become established in the 6th week and the week 11 or 13. I don't remember that, but there are going to be 2 blog courses, like
Exactly.
not just one.
Exactly, but it's like
Okay.
everybody's only participating in one of the weeks. You don't have to participate in both of the weeks.
Okay.
You just are in one of the weeks, and this is yeah. I will try that. It will be much more manageable because we are less people, and then we also don't need so much supervisors. So yeah, if you can manage one of the weeks, this is sufficient. Also, like
Yeah.
for the supervisors.
Okay.
Perfect. Okay, if there are no more questions, I would cut the video so that we don't have the emails and so on in there, and then upload the video. And I'm trying to finish this publications until the weekend, and then I probably will send the list on Monday or Tuesday that you know the publication. It would be great if you can have a quick look before the next meeting over your publication.
And the next meeting is going to be in person? Well, it is
Exactly,
going to
we
be
will-
intended to be?
We will
in
do it
per-
in person. Yeah. The
Okay.
point is like, oh man, if we're all ill, the problem is right now everybody's ill. If you're all ill, or like if half of you are ill, well, like it doesn't make sense. If we're all ill in one room, then everybody's ill over Christmas. That's also not nice. So personally, I was a bit scared like after the last few days because everybody got ill here. So let's see if we all feel good and so on, we would do it in person. But if you really, if you're ill or have like any symptoms or cough, then please don't attend, even if it's a bit of shame. But yeah, the main idea is like, okay, that we have one in-person meeting, but we don't want to get ill. Okay.
Okay.
Okay, perfect. Then, yeah, otherwise, please write me on Slack if there are any questions and so on. The remainder, please try to upload the GitHub things. And anybody who wants to run this model creation script, just get in contact with me. You should just try following the video from last week, and otherwise I can give you a bit of technical support to get this up and running. Yeah. Have a nice evening, and see you next week.
Bye.
Thank you.
Bye.
Bye.
Bye. Thank
Bye.
you.
Bye.
Bye.
Bye.